Well, thank you for coming. I'm overwhelmed by the response to this talk, so hopefully you'll learn something today. I'm going to be talking about large language models, hopefully trying to kind of go in how they work so that you can kind of be more empowered to know that they are not magic, they are maths. So a little bit about myself. I'm a data scientist. I have a PhD in molecular biology, and I'm an ex-cancer researcher who did DNA sequencing and machine learning to kind of do predictions of chemotherapy in lung cancer. I joined Equal Experts about 5 years ago on the Evolve scheme. I'm an incredible roller skater. And my current obsessions are pinball and Street Fighter. As I said before, the aims of this talk is I want to dispel some of the myths around LLMs and how they are catch-all answers to all of your problems and every single business problem going. And I want to do that by showing how they work. I also have a goal that I sort of want to teach you some maths. So it doesn't matter if you don't want to learn maths, you don't need to, it's optional, and I will forewarn you about it. So firstly, what do large language models do? So they are an AI that generates human-like text through being trained on incredibly large volumes of data. Their uses involve text analysis. They can do things like question answering and task execution, and they are the current pinnacle of natural language processing. I'll get more into that in a second. But they are not perfect. They have repeatability issues in the fact that they are non-deterministic in nature, so their output will change. And they do these weird things called hallucinations, where they can give incorrect answers. But in essence, and what I want to show you today is that all they do is predict what the next word in a sequence is going to be. Or to more accurately put it, the next token. Word implies it will keep going. A token can be punctuation or stop talking. So I said LLMs are the pinnacle of natural language processing, but what is natural language processing? It can be things like text processing, like to find sentiment within reviews. It can be pulling out entities from large volumes of text, like companies or countries. It can be taking in documents and figuring out what topics are being explored. It can be things like figuring out aspects of language. Oh, is my microphone going a bit strange? Or applications like translation between different languages and things like speech recognition. It is incredibly hard because there is a lot of ambiguity in language. It's an awful way to communicate. There are multiple different ways of saying the same thing. There are multiple different dialects and synonyms of saying the same thing. You need an awful lot of context around a subject and background knowledge before you can understand it. There's diversity there are different languages and different grammar rules. And finally, on top of all of that, finding good quality data is incredibly hard. So how do we go from this field of natural language processing to ChatGPT? And speaking of that, what is a GPT? So a GPT is a generative pre-trained transformer. It's generative in the way that the machine learning model makes an output in the same form as its training data. So you have an image generating model that is trained on lots of images. GPT is trained on lots of volumes of text and outputs text. It is pre-trained in the way that it's generalized on large volumes of data, and you can download the model as is and use it as is for a lot of broad general applications. And of course, everyone knows a transformer is a parallelized AI architecture for understanding language, right? So what is a transformer? And this is where I have to start giving you a warning that I will start introducing some maths. So look out for this sign. So if we take a step back in terms of machine learning, let's talk about the goals of why we do it. And if we take some, say it's data, and let's start calling it X, and a corresponding answer to what that data means, let's call it Y. We want to apply some general maths, call it function F, to it, to make F wrapped around X, to make some predictions. And the notation for predictions is Y with a little hat on the top of it, because it's like Y, our answers, but it's in disguise. It's wearing a hat. So if we want to start writing some maths notations around that, let's go maths around data equals some predictions, or F of X equals Y hat. Let's start adding some more fields into this. So let's add some weighting values into this that we can start learning and training. So we get data times weights equals prediction. F of XW equals Y hat. Now we can start tuning our model based on these weights to change these predictions. So we can start altering things to make them more specific. So in general, what we're trying to do is make it so that these weights are tuned so that across the entire data set, our prediction, y hat, is as close to y, our real values, as possible. Y is approximate to y hat. That is the goal of machine learning. But how do we train these weights? I've just talked about training them, but how do we train these weights to make accurate predictions? And one method of training these is to use a neural network, which is a type of machine learning and AI that is kind of on its way to large language models and transformer models. But the way in which they work is quite similar. So these take their name from the neuron in the brain, where a neuron will take multiple different inputs via these dendrites, and they will shoot electrical signals down an axon to another neuron, and their outputs affect other neurons in the brain. So if we want to start making this mathematical and artificial, we need a system that takes in multiple different inputs, apply a weighting factor to all of those inputs, and then push an output that can feed to other outputs. And these weights will affect the strength of these different neurons. And because we've now got an output, the great thing is that we can use the output of one neuron for the input of the next neuron, and we can start stacking them together. But first, let me explain how they work. So let's expand on the concept we left behind of maths around data and weights equals a prediction. Let's start adding in a bias term, which is really good for increasing the model's flexibility. So we add some bias. The next bit is, you're going to have to bear with me, is we're going to wrap it around a sigmoid function. And the idea of that is that we're going to shift it so the output is between 0 and 1. We don't want to be dealing with really big numbers. The computer likes between 0 and 1. So I've just written to scale it, but the math notation is to add a little sigma around it. So these weights and biases, again, I hammer home, are what is learned in a neural network. It is what is learned in an LLM. It's what is learned in a transformer. These weights and biases are what are changing. So we can take these neurons, we can take the weights applied to each neuron, and we can start stacking them. So in this example, I want to make a machine learning model that will detect pictures of cats, because that's what we do as data scientists. I want to have a model that takes as its input the pixel values of each pixel in this picture of a cat. I really want to tell me if it's a cat or not. So if it's a cat, it'll say 1. If I give it a picture of a boat, it will say 0. That's my aim. I want to feed, if you see in all of these, every single input feeds to every single neuron, and then the output of this feeds to every other neuron. This is fully connected, and this is a way of having all of the data be connected across the entire network. What we want to start doing is, if we do not train this model and we initiate these weights and biases in this model randomly, we'll get some random answer that doesn't equal it's a cat. So we'll get 0.34 as an output. And what we want is that we want this value to be as close to 1 as possible. So we want to put this back into kind of machine learning talk, I want to minimize the error between my prediction, y hat, and my answer, y, or I want to minimize the loss. An approach of this, which I am not going to go into, is to calculate the loss value with respect to each weight in a neural network, and then start making slight adjustments to the model so that when you run it again, you get closer and closer to your right answer across the entire data set. That is how the training works. It looks at the answers, it looks at your predictions and the real answers and goes, they're different. I'll adjust the model a little bit so that they're closer and closer and closer until the model starts doing things like predicting that this is a picture of a cat based on its pixel values. When you break it down, it's not simple maths, it's not unbelievably complicated maths, but it's done at scale to the point where it can do some incredibly powerful things. So this is a neural network, and this is its application in, say, things like image processing. But how does this work with natural language? And how does this work within a large language model? So I'm going to start introducing this concept which is fundamental to text processing called attention. And I want you to take the sentence, the cat sat on the mat. Now it's really easy to understand that cat is the subject that's being related to sat. Mat is the thing being sat on by the cat, and sitting is what the cat is doing to the mat. It comes very naturally to us. Imagine programming that into a machine. That is incredibly difficult, and as the sentences and the context and the documents get bigger, this becomes harder and harder to kind of keep contextualizing to a machine. So what we need is some way for the machine to focus on the relevant parts of a sentence. And this is a process called attention. It's a learnable method of linking relevant words in a particular sequence together. And the great thing about this is why it's taken off is that it can be done in parallel, whereas previous iterations of this had to be done word by word, making it very, very slow. So the end result of attention is that we want a grid of every single word in our dictionary. In this case, I've just got the cat sat on mat, because we don't need the twice. And what I want is a score of how each word would be similar relative to each other. So for example, here I've got, if I look at cat, very similar to sat and mat. So it's the predictions are that those two things are linked together. If we look at sat, it's going towards cat and on, because you can be on. You can sit on something. So these things have high attention values, whereas cat and on are not particularly highly correlated together because they don't really follow each other. So the end goal of this is that you have a weighting system whereby if I say the phrase, the cat sat on the, you will know that you'll probably start wanting to list things a cat can sit on and not a rocket ship or a toaster. So how again does this work? So firstly, we want to start representing these sentences as vectors or lists of numbers through a process called embedding. I then want to take two weighting vectors and start applying them to my data. This is the complicated bit, so don't worry, is that I will then multiply each element of the list together and scale it. So that it's add it together and then scale it. And I'll make sure that all of the values equal 1. Lost? Me too. But the great thing about this is that this weird function where you make sure everything equals 1, or the softmax function, means that every single value in your vector, so the cat sat on mat, is now a probability. It's a probability that's been weighted that can then be reapplied to data. So now you have a way of weighting each word in your list by the words that have already come up. This is how attention can work, and this is how you can start learning the probabilities between words and what is the next sequence that can come up. So this is an example from Frozen where they shout, I finish each other's sandwiches. And you go, well, something's kind of gone a bit wrong there. But what you can do with this is you can take these probabilities and apply them back to another weighting plus data pair, and then you start getting actual values of what your most probable token is from the data. I'm going to go back into maths. Feel free to go onto your phone. I won't be offended. So this is the attention formula with some minor alterations to make it nicer to see. We have our data times weighting pairs of X being our data and two weighting values, Q and K. I'm going to add this weird dot between them, which means the dot product, which means that every element in the list that is XQ and XK, I'm going to multiply them together and then sum them together. And then I'm going to scale that value so it's between 0 and 1. I'm then going to make sure that all those values are switched so that when they're summed together, they equal 1. That is how our probability is calculated. That is how we get a relative probability for each word based on each other word. And that gives us that grid that I showed at the beginning. Then apply that again to another data pair, XV, and we get what the next probable token is. That is the maths behind how an LLM predicts the next value in a sequence. That is rooted purely in data, and it's rooted in 3 weighting series. Matrices rather, or tables of values. This is how context is achieved in a neural network, in a transformer and in ChatGPT. This is how it can accurately predict the next word. So that's great, but why is this relevant? So if I wanted to train ChatGPT, I'd first need millions of pounds, but to do this, if I fed a model sequences of text and took away the last token, so the last word in the sentence, and then I told my model to predict what that word was. I've then got my prediction and my real value. I can compare the two of them. And then those weight matrices in the previous formula, I can update them based on how different they are from giving the real result. Just like in our neural network example, you can start tweaking these weights. And given enough time and given enough data, you can get a weighting system that will accurately predict sentences in a way that mimics human language. That's what the basis of the models underneath ChatGPT do. This is called the foundation model. And if you give it large enough volumes of data, you can have responses that change depending on its contextual, on its context. And so you can get knowledge about different subjects in a way that makes you think it knows a lot of things and is an expert on everything. Or in machine learning talk, it attends to different words in this. It's just applying this weighting system differently. But ChatGPT doesn't just predict the next word in a sequence. You can ask it questions, you can get it to do tasks, you can get it to follow instructions. How does it do that? So once you've got this foundation model that just predicts the next order of a word, you can do a second round of fine-tuning. And this time, say I wanted to make it answer questions, I get a data set that has pairs. I have a set of questions and I have a set of answers. I feed it the questions and go, predict the next words. Then look at the answers and go, well, they're different. Adjust the weights again. And all of a sudden, after several rounds of retraining, it's got used to how a question answer series works. And it will start now answering questions rather than just making sentences. You do that again with an instruction following data set and it can now follow instructions. You add in additional components like grading responses compared to human responses in a process called reinforcement learning. And you've got multiple ways in which you can add this complexity to a large language model. I did mention at the beginning, though, that they have a downside for applications in that they are non-deterministic. I'm going to go through what that means and why, but then kind of show that it's not something to totally worry about, well, maybe. So you can ask an LLM the same question multiple times and it will probably give you variance on the answer. It will not give you the same perfect series of words every single time. And there's a number of factors at play here and there's a number of things that you can control when deploying your own LLM. One most people talk about is called temperature. And this is an additional value that you can add into that softmax function. So the thing that made everything in a list equal to 1, you can adjust that slightly with this temperature. With a low temperature being a more conservative answer, meaning that the model picks high probability tokens for the next sequence, and high temperatures adding a bit of diversity to sentences. Another method being top K sampling, which is it picks the top K most probable tokens rather than the entire English language or every language, and tries to predict the next values from that. And this has a great thing of introducing some randomness while still giving it highly probable answers. And the last one being this process called nucleus sampling, where you set a threshold and it picks tokens until this threshold is met, and then picks one of those values, which is great because it has a trade-off between high probable tokens and that more diverse tokens. And these things all sound great, but apparently non-determinism is a problem. Like the computer doesn't say the same thing every time. But in training and in language, adding this randomness actually improves the text generation. Have you ever played the predictive text game where you just press the next word on your phone and it just gets stuck in a loop and just says the same thing over and over again after a certain amount of time? If you go for just the highest probable token every time, you end up in loops and ends prematurely. It doesn't make particularly great sentences. So this is a trade-off about adding you add some randomness and you actually improve the output. Humans don't follow the most probable thing. So language doesn't, so the LLM doesn't. So hopefully I've sort of gone through how they work in a way that shows that it's applications of maths. I just want to go through now some uses of them. So the first thing I always get told is I don't want to use ChatGPT because it gives really broad, generic non-responses. I just kind of want to go into that a little bit. So if I ask ChatGPT a question about something, say this is a graph of the typical knowledge a person has about a topic, about the number of people. At the top of this graph, you've got the typical amount of knowledge that someone knows about a subject. Now, around here is about 68% of people. And LLMs, being trained on a lot of data from the internet, are trained on the vast amount of public knowledge. And most people don't know very much about a particular topic. So this height of typical knowledge is probably low. So when you ask a question, it's going to use this knowledge. But when I ask a question to ChatGPT about something, I don't want typical knowledge, I want detailed expert knowledge. So how do I tap into this expert knowledge, which is about 2.5% of people? Now, my preference for this is to start using things like LLM personas, where you add a bit of additional kind of information to the LLM that starts giving it more context. So in my example, I like to pretend to tell it it's an expert talking to another peer. So I've got, you're a hardware architect speaking to another expert. Explain to me why a GPU makes gaming better. You'll get a much better answer than just go, explain why a GPU makes gaming better. That kind of thing really impacts the level of detail you're going to get in an answer. And the rationale for this is that without that additional prompting information, the weights within the model are associated with giving the general response of the general public. You giving this persona starts shifting the context of the model so that its attention is now focused on information around the expert opinion of it. Yes?
Why don't they build that sort of hyperprompt into the fine-tuning stage so that the chat always responds to that answer?
Because it's probably not as it's probably not generally as nice, or they might find that it will give lower. Its ability to predict is lower than expected. The short answer is I don't fully know why they don't do it, but yeah, in general across the entire data set, if most of it is the normal response, you're only training for 2.5% of the response looking for an expert. To talk back in the AI kind of mathsy space again, when we're adding these personas, what I'm going to say is we're filtering the latent space of the model, which is the compressed representation of the weights and the data within the machine learning model. Another question that comes up is, can I use my own data? Yes, you can. There are a few different ways. So the most common one that came up was this system called Retrieval Augmented Generation, or RAG. And this is using a document store to hold all of your knowledge. You have a vector database that holds the kind of attention-weighted embeddings of your documents within a store. And then you give a prompt to a system and it will filter this dynamically depending on the similarity of your query to the documents within the store. It'll retrieve documents it thinks are relevant and push them and your query to the large language model. The large language model will then generate a response and based on the documents that you've given it. This is a great application because it's very, very versatile. Its pros are that you can use a model without needing to retrain it. You can use an off-the-shelf LLM as well. You can also use a smaller one because it doesn't need this giant context and large amounts of weights. It also scales really well. The document store just needs a retrieval step and then pushes a certain number of documents to the large language model. It's also more rooted in fact and less likely to hallucinate. The downsides, however, are this system adds latency. You have an additional retrieval step that you don't if you just ask an LLM a question. That adds latency. You live or die by the accuracy of your retrieval. Bad document retrieval means you get a bad response. The architecture is more complicated because you've got more moving parts. And because it's only picking what it thinks are the most relevant couple of documents, it really struggles with multiple document context ability. So it's versatile, but it's slow and it's a bit more expensive to maintain. Another method which is starting to come more into fruition is fine-tuning a model. So this is giving another rate of retraining a large language model or a section of a large language model on a much smaller but specific data set. And now this starts specializing the model around a particular task, which makes it highly accurate and great ability to contextualize across multiple documents. Fine-tuning, however, is quite expensive, although that cost is now dropping, but it's great if you have a specific application that you want to do or a specific task that you want to do. To go into the pros and cons again, it's a simpler architecture because you have no retrieval steps, and the LLM can directly access its knowledge within its own kind of knowledge base, and it gets deeper context understanding. But the cons is that the knowledge is now fixed at the time of training. If you add more documents into your document store, you need to retrain the model, which if you keep doing that over and over again, gets very expensive in terms of retrains. It also doesn't scale as well, because as you get more and more documents, the cost associated with training starts to increase. And this method also has a higher tendency than a RAG-based system to hallucinate, because it's just using its internal knowledge. Another method which I've found really fun and great to use is using these concepts called user agents, which is stacking LLMs together and giving them tasks where they can all subset the task, and it allows them to perform much more complicated tasks. You can give each LLM a different persona that they take on, and they will do things in circles and chains that will massively increase the complexity of just using one LLM on its own. The massive, massive drawback is that using this is slow and expensive. I made a workflow that took 7 minutes to run and cost £3 a run. So it's not scalable. And another downside is that with this system at present, you're currently using the same LLM, say ChatGPT, or GPT-4 rather, with different personas on top, like it's wearing different disguises and putting different hats on. So there's some applications, but where are we going next? One place I think we're not going next is continually making bigger and bigger models. I think we're at 70 billion plus parameters at the minute, so 70 billion plus weights and biases that get trained and tuned. That's a lot, and that's currently trained on a large proportion of the internet. Adding more parameters and more data is going to give a much more diminishing returns on performance. We're not going to get a massive leap in performance with this method, but we are going to get a massive leap in complexity and cost of training. Training these systems as well has a massive environmental impacts. I think it was several £million in electricity costs to train some of these models. And multiple companies are now doing this, and we're now getting fine-tuning systems. So the bigger these models get, the more this is going to cost for less return on ability. You might get yourself in a situation where you start now overfitting, which is a concept of you start modeling the noise of data rather than generalizing to language. So you might actually get worse performance the more parameters you add in. And there's alternate approaches that are starting to come up as well, which are about being a bit more frugal with data, like model pruning, quantization, which has started to gain a lot of traction, which is essentially rounding values to make them smaller in memory. That's essentially it. That's why you need larger systems to do this. And model distillation as well can help improve model efficiency. Another area that I think is going to be of massive interest is the concept of hallucinations. So this is, again, where an LLM generates a plausible sounding response that is completely factually incorrect. It greatly limits the trust that people put in these models, and therefore you get less adoption. And for a large tech company, less adoption is less profit. And so it's a very large active area of interest and research around how to understand and reduce hallucinations. And just so,
Just a question. So if everything is trained on the data, basically statistically possible next word or statistically possible result, how the hallucinations occur, it adjusts like kind of this incorrectly assigned probability, like low probability answer?
Yeah.
Or is it something more complex than that?
The current thought is that it's assigning the incorrect probable token. I'm not sure if there's any other thoughts on if there's any other methods. But typically these hallucinations come for if you ask it a question that it's never seen before, or a really niche question that it hasn't quite learned to generalize yet in terms of its data set. So you go, oh, how would I send a corgi to the moon? And it goes, I've never seen that before. And it'll just make up a response. It will always give a response. It will always try and make the next tokens. If it's never seen that answer before, it'll try and figure out what its most probable thing to say is. And that's where it starts hallucinating.
So it doesn't hallucinate on like more common knowledge that has a large data supporting the training.
So that becomes interesting when there's a lot of common knowledge about a topic, if there's conflicting information. about a common topic, it might pick a bit from both sides of the argument and get it wrong that way. That's always an interesting point where it will piece together both sides of an argument. There's not really a good way of determining a hallucination right now, other than a human going, "That's not right." Yeah. But in terms of an area of research, I just want to highlight a different area of machine learning research, which is video generation. And these two state-of-the-art demos are a year apart. The really cursed video of Will Smith eating pasta is from 2023. And this beautiful, almost Pixar-like animation, which has a lot of caveats associated with it right now, I will not lie, is almost Pixar quality and is from 2024. These are a year apart in terms of an incredibly active area of machine learning research. And there's much more money in LLMs than in diffusion models. I think as well in this, we're going to see a much more adoption of open source models. So the great thing about an open source model is you get to retain complete data privacy and complete ownership of your large language model, rather than send things over to OpenAI or Google or whatever. The trade-off typically has been that OpenAI's models have been above and beyond everyone else's, but that gap is closing, and open source models like Llama 3 and Phi 3 are closing the gap in terms of this, which means that deployment, yep.
Just a question on the RAG stuff that you showed earlier, that feel that some of the columns to be listed would be basically abstracted away, taken care of by, say, in the same way that
Oh, potentially, yeah. Potentially, yeah. So some of the disadvantages of the RAG system being like the ability to not really having the ability to have a large context, and so you miss out on, you can only answer simpler questions. The models are getting larger and larger context windows, and Google are patenting something called an infinite context window, where I'm yet to research, so that might go away.
No, like you also listed, like it's complex and there's maintenance costs and things like that. So obviously those things will need to be taken care of.
Potentially, but I still think that adding in a vector store and a retrieval mechanism will always cost more than directly querying a LLM. It's just, if you're deploying your own LLM, that'll cost more than the retrieval costs. Like I don't know how that one's gonna pan out. But these kind of open source models can be fine-tuned, whereas like things like OpenAI's models cannot. They can be, but you're not really in control of them in the same way. And then additional efficiency techniques like quantization mean that you can start fine-tuning these models with much less system requirements than previously. Another area I think is going to be of interest is again in user agents. So as I said before, typically when you use user agents to adopt personas, you use the same model like GPT-4 and you give it different prompts to say, you're a BA, you're a delivery lead, you're a data scientist, and it just sort of wears different disguises. And I found a data set full of people pretending to wear disguises for machine learning purposes. Being able to have truly different user agents that are different models, some that maybe be fine-tuned, some with RAG ability, some with like high context and broad applications, means that you can get truly different knowledge bases and truly different contexts on situations, so you can get even more complicated instruction following and task completion. The model distillation is another method, which is where if you have a deployed incredibly large model in production and you don't really want those ongoing costs, you can store the query that's being sent to a large language model and store the answer coming from it, and then you've got a pair again to do fine-tuning on a smaller model, so that you can start learning to make this small model act like the large one for your specific task. So you can decommission your giant model, replace it with a smaller model for smaller tasks that might actually be more accurate, and repeat this process over and over again until you have the minimum size model required to do your task. One that I think you might not have seen that I am quite excited about is this concept of latent space understanding. So I mentioned before that when we are doing the personas to pretend to be an expert to get a good answer, I'm filtering the latent space of the model. I'm doing that sort of blindly in my example, where I'm hoping that by pretending that I'm an expert hardware architect, it will give me a good response. This is the field of understanding how those interactions within the model work, and so that you can start altering it purposefully. This field is very much in its infancy, but in the area of image generation in diffusion models, you can, if you understand some of the latent space by some incredibly complicated maths, you can add weighting factors to your model in terms of its image generation to go, I want to make this person older, or I want to turn this person into a woman, or I want to make this person's nose redder. And understanding how this almost black box interacts in this weird latent space, you can start customizing how the model is generating an image. You apply that to an LLM. Yep, Harry?
Like feature engineering, you manually looking at the space and say, oh, I can see that this dimension will
Sort of, yeah. So once you've got the with a diffusion model that you've got, you can kind of loop through and see what weights are being applied and what neurons and stuff within the model are being triggered, and you can then from there see what the values are and go, oh, in terms of if I want to start moving this way, these factors change. So and then you go, once you start learning that, you go, oh, I just apply this additional list of strings to all of my values, and it changes the output in a known way. You apply that to something like a large language model, and you, instead of guessing when you do prompt engineering, go, oh, I want to make this sound more professional. Let me turn up the professional dial. I want to make this a haiku. Let me turn up the haiku dial. Decided it's in French. And you can now alter how the model is performing in a way that you will know its output, rather than when you prompt engineer, you are sort of guessing and hoping. The great application for this is that understanding these latent spaces means that you can effectively add guardrails. Guardrails currently in an LLM like ChatGPT are a bit unknown because OpenAI will not tell you how they work, but everyone sort of thinks that they're if-else statements on the end of a prediction that go, yeah, probably shouldn't send that to the model. Understanding this latent space, you can see that the model has accessed an area that it probably shouldn't, and you can either delete those areas during model tuning, or you can make sure that it adjusts itself out of it. But you are now in control of this. So, in conclusion, LLMs are thoroughly grounded in maths and are not magic. Attention weights are part of one of the ways that a model learns knowledge and context. With a RAG-based system, you can flexibly retrieve documents and knowledge within them for simple contexts, but for more specific direct retrieval, you can use fine-tuning. Agents can combine all of their efforts together to solve much more complicated problems. And in the future, the field of LLMs is massively growing and will only continue to grow as the hype further increases. Thank you.